In the previous video, we briefly discussed the advantages and limitations of crystalline silicon as a solar cell material. In this video, we will discuss the basic properties of this material, such as the crystal structure and the orientation, the energy dispersion diagram, and the absorption coefficient. The element silicon is a metalloid with atomic number 14. It has 4 valence electrons and can therefore make covalent bonds with 4 neighboring atoms. The crystal structure of crystalline silicon is cubic diamond. This diamond structure is described as a face-centered cubic lattice, which is a cubic lattice, with atoms placed at the center of each face as shown here. The cubic diamond structure has 4 more atoms in the unit cell. The lattice spacing of crystalline silicon is 0.543 nanometers. When focusing on one silicon atom, we see that covalent bonds of this atom with 4 other silicon atoms form a tetrahedral structure with a bond angle of 109.47 degrees. We now return to the unit cell. In this unit cell, many different lattice orientations can be found, which are indicated as the orientation of a lattice plane with respect to the lattice. Using the so-called Miller indices, a vector representation describing the orientation of these lattice planes can be given. For instance, the lattice plane with 1, 0, 0 orientation is shown here, with respect to the atom marked in red. Another often used orientation is the 1, 1, 1 direction as shown here below. These two orientations are most commonly used for crystalline silicon solar cells. The difference in lattice orientation is visible at the surface of the material. When we first look at the 1, 0, 0 orientation, we see that each atom at the surface of the crystal is back-bonded by 2 silicon atoms. As each silicon atom has 4 valence electrons, this means that this surface atom has 2 electrons that are not shared with another silicon atom. These are so-called dangling bonds, which are marked here in red. For the 1, 1, 1 orientation, we see that each atom at the surface of the crystal has 1 dangling bond. Each surface atom is thus back-bonded by 3 neighboring atoms. Later in the course, we will discuss more differences between these two lattice orientations, but for now, we first discuss briefly the effect of the lattice orientation on the energy dispersion diagram for silicon. In order to simplify our discussion and to get some intuitive idea about the effect of the lattice on the dispersion diagram, we take a look at a one-dimensional lattice of equally spaced atoms of a distance a apart. On atomic scale, the behavior of electrons is described by quantum mechanics, in particular as a solution to the Schrödinger equation. The atoms in this one-dimensional lattice form a periodically varying potential. It has been shown in the literature that the solution to the Schrödinger equation for this situation is a wave of the following form, with k the wave factor in units of inverse length. This function is called a Bloch wave. We can clearly see that by increasing the atom spacing, the wave factor of the wave solution cannot be constant, but should decrease as the wavelength needs to increase. Now that we have seen the solution in one dimension, you can imagine that k will also be affected by the atomic arrangement in 3 dimensions. The solution to the Schrödinger equation in 3 dimensions is beyond the scope of this course. But we can already see from the unit cell that different directions will give different atomic arrangements. As k is directly related to the energy of the plane wave, these different atomic arrangements will result in different available energy states for electrons in the lattice when considering the different orientations. In solid-state physics, it is common practice to consider the so-called reciprocal space. In reciprocal space, or K space, the first Brillouin zone represents the unit cell as shown in this illustration. The electronic band structure of a periodic material such as crystalline silicon is obtained by finding solutions to the block wave functions in the first Brillouin zone, as these solutions are proven valid for the entire medium. The Greek letter gamma represents the center of the first Brillouin zone. The Greek letters lambda, delta, and sigma represent different directions towards specific points on the reciprocal lattice indicated by L, X, K, and U. The lambda direction in reciprocal space is equivalent to the 1-1-1 orientation, the delta direction to the 1-0-0 direction in the lattice. Solving the block wave functions, an energy dispersion diagram for silicon is obtained as shown on the right. The band gap of the material, here in white, can be defined as the energy difference between the maximum of the valence band EV and the minimum of the conduction band EC. However, when we take a closer look, these are not located at the same point on the reciprocal lattice. This has an important consequence for this material. Silicon is what we call an indirect band gap material. This has implications for the absorption of light, as photons can only be absorbed if the excited electron gains momentum in the lattice to reach the conduction band. This momentum can be transferred to the electrons by lattice vibrations, which are also called phonons. Since this interaction is required and the energy and momentum in the crystal should be conserved, the light absorption of an indirect bandgap material such as silicon is much lower than a direct bandgap material, as we will see in a moment. If we look at the energy difference between the lowest point in the conduction band and the highest point in the valence band, then we find that the indirect band gap of crystalline silicon is 1.12 electron volts. However, silicon also has a direct band gap of 3.4 electron volt that is located at the center point of the reciprocal lattice. This implies that the absorption coefficient of the material is therefore increased by orders of magnitude for photon energies exceeding 3.4 electron volts. The indirect band gap of silicon thus has a consequence for the absorption coefficient of this material, as displayed in this slide. The attenuation of light in a material is described by the Lambert-Beer law. It relates the intensity of light at a distance x from the surface of the material to the incident intensity I0 for a given absorption coefficient alpha. A low absorption coefficient requires more material, i.e. a thicker layer, to absorb a larger fraction of the incident photons. For instance, at a wavelength of about 800 nanometers, we see that the absorption coefficient is about 1000 inverse centimeters. And then we need a layer of silicon with a thickness of 23 micrometers to absorb 90% of the incident photons. If we look at a wavelength of just below 1000 nanometers, the absorption coefficient is an order of magnitude lower at about 100 inverse centimeters. And in this case, we need a thickness of 230 micrometers to absorb 90% of the incident photons up to a wavelength of 1000 nanometers. When we compare the wavelength-dependent absorption coefficient of crystalline silicon to direct bandgap materials such as gallium arsenide, indium phosphide and germanium, we can clearly see that the absorption coefficient of silicon is up to 2 orders of magnitude smaller up to the direct band gap of 3.4 electron volts. This corresponds to a wavelength of 365 nanometers. As an example, the thickness of germanium, which is also an indirect bandgap material, only needs to be about 2 micrometers in order to absorb 90% of the incident photons at a wavelength of 1000 nanometers. Another consequence of crystalline silicon being an indirect bandgap material is that the radiative recombination rate is low. This is the recombination process in which an electron in the conduction band and the hole in the valence band recombine and emit a photon carrying an energy comparable to the bandgap of the material. However, when the momentum of the electron and hole are not equal, the process should include a phonon to conserve crystal momentum, which is less likely to occur. For this reason, radiative recombination rate can be neglected in indirect bandgap materials like silicon. The positive side is that the lifetime of excess charge carriers and thus the diffusion length is long, since they are less likely to recombine. To summarize this video, we have discussed that the lattice orientation of crystalline silicon has an effect on the energy dispersion diagram, making silicon an indirect bandgap material. The absorption coefficient is therefore much lower than of direct bandgap materials, such that a thicker layer of material is required to absorb a large fraction of the incident light. On the other hand, radiative recombination can be neglected in crystalline silicon, as a phonon is required to conserve crystal momentum, making this recombination mechanism less likely.